Hello and welcome back to another episode of Getting into Git Oxide. Hey, and welcome back, Sydney.
Hi, Sebastian.
And today we are still not yet quite there working on Git describe like functionality, even though we could start, because this thing happened, like checking out the Linux kernel under a second. And all this is great. I mean, that was the result of the last week's work, more or less, and checking it out in 847 milliseconds is pretty rad already, but the overall efficiency is just 60%. This means that if a single core would scale linearly, then we would expect 40% more performance here. So 214 times 8.5, so 1.8 gigabyte I would want to see here for perfect scaling.
Okay, so the parallelization isn't working as efficient as expected, basically.
Yes. And this can have two reasons, of course, Git Oxide or the file system, or a combination of both, because this is on tempfs here. And tempfs, sure, writes into RAM, right? But it's still a file system. So it still has to do file system specific things. And the more you do in parallel, the more your cores have to work, and it goes to the kernel, and it's potentially expensive. Still, you pay for it, but you pay much less for tempfs. But I was thinking, yeah, maybe there is a way that Git Oxide could be faster, especially after I've seen this. So somebody tested that also with 10 cores limit on different CPUs, and the Intel CPU here can do the same work in 550 milliseconds, and that AMD monster, or whatever it is, 402 milliseconds. And what really caused me to look into this again is that this processor with 24 cores, 24 real cores, is only 20 milliseconds faster than this. And that's a bit strange. Like, does it really bottleneck on the file system so much that it can't scale anymore? Or does it bottleneck on Git Oxide? And I have a feeling it could be bottlenecking on Git Oxide, especially as you approach these small times with millisecond levels here. Like 400 millisecond, that's not a whole lot of time, especially when you think of task switching and so on. That can take, I don't know, that can take a couple of milliseconds, I guess. So you kind of get in the range of you better do that perfectly, the parallelization, or you can't really scale up. And even though obviously Git Oxide already scales much better than Git itself, like Git on this machine I think is 3 times slower, or 4 or something, so that really is significant, right? But we still don't really get to the future of CPUs, because in a way that is the future. Like ordinary people having 24 cores, or I having 24 cores in my laptop. So I don't have that right now, but ask me again in 6 years or 7.
It's going to be there, yeah.
It's going to be there. So Git Oxide should really scale better, even though the file system kind of is the bottleneck, but also it only still is the bottleneck. Who knows what's in 7 or 8 years, and now we already have like 6-7 gigabyte per second write and read speeds, and it's just insanity. It really is. So yeah, gotta scale with that. So what's the problem with Git Oxide? Or what is there even to optimize? And we can have a look at this and understand that a bit better, and maybe even give a different approach a test run just to get a first measurement. We don't have too much time for this, but I'll try to guide you through the basics anyway.
Good.
To see what we have here. Okay, so there is this quite simple fan out, fan in parallelization thingy here, or utility in Git Oxide that is used wherever you need parallelization. And what it does is it gets a bunch of input and then creates a bunch of threads according to the thread limit, and then it sends that input to all the threads through a channel. The consume function here is called on that input, and it produces an output. There's some thread local state to work with, but it doesn't matter. That output is then sent through an output channel to a reducer who aggregates the result and returns the result. And it's literally just input producer, bunch of threads, They pull input from that channel, which is a source of contention, because that needs locking mechanisms, right, to make sure only one thread gets the price.
Right stuff.
Right stuff, exactly. And the same happens when sending the outputs. There might be some contention, and there might be some blocking, depending on, there could be some congestion there. And maybe it's a bit hard to visualize with just me fumbling with hands here. But if you think of like a large amount of threads and one producer, then the larger that amount gets, then, there's only one item going through that channel at a time. So these threads, they have to kind of wait their turn until they can actually pull something out. So the producer here is trying to produce as fast as possible. And there is a buffer even for, there's a buffer even here that means for each thread that we have, there's a slot in that pipe or in that channel so that the sender doesn't have to wait. So in theory, we can just quickly fill the whole pipe with items because we have enough buffer space here. For each thread is one slot, and then the threads can in theory quickly pull items off that queue. But that's still contention because it's only one at a time just by definition. So the more threads you have, the longer it will take that mechanism to feed all the threads so that they can start working. And once they start working, this takes time. And then probably there's much less contention on that channel as well, assuming that it produces fast enough. And in our case, that's fine. This thing produces fast enough because all the data is already there. There's no computation done. Okay, so you can remember, I think, that there is contention to get the thread started, and that takes away from your overall performance. Just imagine you pay 50 milliseconds more than you have to for feeding everybody because you have 50 threads or something. And then, if you're in the 400 milliseconds space, then that's already 12.5%. It's quite significant, I think. So that's a bit annoying. And then for the output, one could assume that there is no contention because they will start producing output kind of randomly, and there's always enough buffer space here so that the reducer can aggregate the output. So that should not be a problem. Also, everybody gets work as much as there is. So it's not that threads don't get anything to do just because, they will always get something if there's something to work on. And ideally, threads keep working pretty well. But that initial time for ramping this up, that could be an issue with the system here. And also the synchronization that happens here through the mutex that probably is somewhere in that channel, just by its very nature. Yeah, so I thought, how can that be better? And came up with this. So that's kind of tailor-made to support the worktree parallelization. So its input is mutable even. And the idea here is that you don't have channels. Going back here, using channels is basically the Go's preferred Golang's preferred way of dealing with concurrency, right? You share by communication, and that prevents you from running into all kinds of issues, creating new ones. But at least you don't have to protect your memory and have to make sure nobody writes the same memory at the same time, which you get when you share memory. However, sharing memory is exactly what this thing does, because that's the only thing that makes the initial run-up time disappear, because then you can just distribute your threads on that input slice using some algorithm, which probably is just round robin, one thread, next thread, and then you keep going, right? So it's just boom, 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 and then they skip to the next one, and each to the next item that has their specific offset, so to say. So it's like, yeah, it's like having a bunch of items and all your threads, they start here. And then if they would finish at the same time, the whole bunch of threads would go to the next bunch of chunks, so to say, right? This is how you can imagine it. And they never overlap that way. And that's the general idea here. So basically, if they would finish at the same time, bang, 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 and the last chunk is a bit less probably, so some won't have anything to work on. That's fine. The others will. So in theory, everybody has work. Practically, now you have an issue with busyness. If some threads have more to do, then they might be slower than others, and others might finish earlier. And then there's work left to be done, but they won't be able to pick it up because they have no channel to pull work from. So, trade-offs.
I guess it depends on the implementation of how they choose their work, right? Right now it's, I guess, pretty simple with just an initial offset and an interval that they have. But if they could do this in a smarter way, then I guess this would be possible, right?
Absolutely. And it's already implemented in some way. I don't know if it's good or not, but it's implemented. But I just want to highlight that work stealing you get effectively with this mechanism. Assuming your chunks of work are small enough, then you get efficient work stealing here. Because
it's automatically being filled by the next one that frees up, basically.
Yes.
So it's always kind of optimized towards.
Yes. And sure, you can only steal stuff or you only get work in terms of the chunk size, but this thing doesn't know about chunks, it just knows about inputs. Chunks is something that you do internally, and you tune that. If you want to have, if you want to do one item at a time for checking things out, you can, for example. It might just be more overhead to push that through the channels and so on. So you, in some way, you pay. There's this trade-off again. This is why I use chunking mechanisms here to have like 100 entries to check out in one chunk, so that every thread gets some more work to do. But here you don't have that, unfortunately. But it's implemented here. It's some probably stupid and naive way, but I don't know better. First of all, the way this whole machinery comes to stop and so on, it works kind of differently, because observability of the whole operation is different too. Like here, there is a receiver for results, and these results are received in real time. So the reducer gets fed whenever a chunk is done. And then this means you can, update progress information and so on. And you can also decide to abort. Like this one here, it can abort the whole operation and will just naturally happen, because once channels go down, once the sender goes down, then all the threads naturally come to an end. And that's pretty cool, because then this looks like that. Oh yeah, here's a loop. And we receive input and we send the output. And it's so simple, that idea. And that makes it also nice to implement. So this is why this is the first one to implement. And now if you look at this monstrosity here, you already see why. Like now you do so much by hand. And observability is obtained through a callable, or through a closure that I just call periodic here, which is called periodically, and it just returns a duration to say how long to wait till the next time it will be called. And it's expected to have all the state it needs to make progress updates work. So now it's all about shared memory. It's all about having the consumers or whatever share enough state or update enough state using atomic ints or something to count things, and then this periodically called thingy here is then able to, fill or to own things like progress reporters and can just load these atomic integers and put that into the progress itself. And this being an option means that it can decide to stop everything to abort if it returns none, because maybe it knows something that is part of its internal state. It can just, like, the user asking for interrupts, for example, then this is done like this. And the interrupt handling here, like how to stop all the workers, for example, if there's an error or if interruption is requested like this, then the stop everything variables just, turned on, just put to true. And then every thread is supposed to stop down. So they have to check this periodically as well here. And that's how that works. And the worker code itself, it's much more complicated. I mean, what I like and what I think is a big, I didn't have it like this the first time I wrote this, but over time it developed because I realized, yeah, let's use ranges properly. Because here all we do is we started our thread ID, go through the pre-computed amount of chunks, and then we step through it instead of by the amount of threads.
Yeah, so thread ID is the offset and then threads is the interval of the step count.
Yes. And that should work. Now that I look at it, I think, oh, maybe it doesn't work. I only have one test. I really was lazy with tests here. I really wanted to get it to work on the real thing real quick. But yeah, anyway, but that's the general idea. And at least in my simple test, that seems to be working, even though probably there's some math error that I put in here. But yeah, that's that. It checks for interrupts, checks for whether it should stop or not. And then we have a results array. So for each input item, we have one possible result. And that is done in a way that result is protected by a lock, so that in fact it's impossible for us to, by accident or by bug, work on the same thing with multiple threads. Like even if this would allow multiple threads to work on the same thing, we make that impossible because we still have to acquire a lock for the result. And that could tell us that somebody has already acquired the lock or that it's already done. That result array, that is a vector with a mutex and an option that has the result in it, which is as much as we are thread safe and only one at a time, but there might not be a result yet, which makes sense for this kind of interaction that we have here. And now the algorithm starts that is all about work stealing. Because we are able to break out of this first attempt, let's say, where we have the regular go chunk by chunk kind of way of working. And when it encounters that somebody already is occupying your result, so somebody has stolen your work right now and is working on it, or somebody already worked on it, then you just break out of this normal mode and go into the work stealing mode. And that's what comes next. But if you happen to acquire a log and there's nothing done yet, then you would be getting your input chunk and you can let the closure, the processor actually work on that chunk, get the results. That's just some internal bookkeeping here to understand how much work there is left. We want to abort and want to make everybody abort if our result is erroneous. This is why we do this like this, but we will always remember the result. That's important for later. So this is why we have to kind of interleave this a bit, that we look into what's there, then we store it, then it's kind of gone and it's in an option then, right? This is why it's a bit harder to obtain then. This is why I do it like this. I don't know if you're familiar with this syntax, if you've seen that before.
I was just about to ask. Yeah, I don't think I've seen that before.
I mean, you can tell what it does, actually.
Can I?
Yeah. Like, at least here, you see how it's used, right? It's not far away. So there's not more to it. It looks like magic syntax, and it is, but what it does, like if you describe what you see without having to explain it, what happens?
Yeah, so down there you're getting a reference to result, or this variable name.
I
and
think
you store the option in it, but it's still, yeah.
I think you're trying to, you're like, maybe you have issues understanding how you can have a none there somehow. Like, how can you assign a value to none? Or how can you bind a name to none, right? Is that the issue? Like, it's none, so how can you how can you assign that or something?
Yeah, maybe. I'm also confused by the res variable at the top there.
Oh, right.
Is that related, or is that completely different?
It's related as the result is wrapped so many times. It's in a mutex, and here we get a borrow, read-only shared borrow of the mutex. Then we try to lock it. Then we bind the result space. Like you can see it as we bind the memory location that is supposed to contain the result, and it's an option something. It's an option result.
Right. So it's like a reference, basically.
Yeah.
You're creating a reference to that memory space.
Yes. And I can, of course, overwrite that with something else, whether it's none or not. And this is what happens here. I don't have a value to work with because it's just none, but I don't care about anything. I just want the option itself. And I want to overwrite that.
And how does that differ from the none case below then?
From the none case below? Where?
Wasn't there another case?
Yeah, here.
Oh, sorry, that's two yeah.
Blocks.
Okay.
Yes. Yeah, that's the lock not being present or not being acquired. Yeah. Okay.
I see. Okay, then that makes sense. Yeah.
But I see now where you're coming from, that there is lots of res, but it's very intentional to whether the name is good or not, like for results, abbreviation, whatever. That's another issue, but at least it's the same in principle, and that's why it has the same name, and we just shadow what's on top. And I prefer that kind of confusion over the confusion you get by trying to accidentally access the top level result lock, or however you would call it. Then you have to find all these new names, right? And try to use it in the wrong location because it's already bound to the other res option, whatever you want to call it then. And then, it's just the Rust way. For better or worse, I don't judge. It's depends on where you're coming from. But once you got used to it, it's preferable, especially if I compare it to the alternative. But yeah, and this is why I just assign a sum here, because yes, we have a result now. There is something we want to assign, and that's it. And then if you want to abort, we just signal that to everybody essentially, so that all the threads stop working. And what we want really is to be responsive to user input. And if the user wants to abort, that should happen quickly. And it happens as fast as a chunk can be processed. So if chunks are too large, work stealing isn't good, and real-time interaction isn't that great. So small chunks are in every way beneficial, but of course, trade-offs again. Yeah, and now work stealing mode. Okay, so there's a fancy stupid algorithm that I can best describe with hands, I think. So imagine, let's say we have 5 threads, 1, 2, 3, 4, 5, and you imagine them being stacked on top of each other. And it's like, you know, there's like a matrix, and each one has a bunch of work. Okay. Okay. It's like a racetrack with little dots on it. It's Pac-Man just in one direction. And then they march and eat up the work. And as one is, let's say thread number 1, or the first thread we have is done working and gets into this work stealing mode. Now it's the first thread. And there would be still like 1/4, 1/5 of the work, 4/5 of the work would be left. And this means that there's a lot of work, so there should be a lot of time for it to find work. And this is kind of signaled by fuel. So that's a bit of a tunable. If fuel says how often can you try to find work? How much can you jump around? And whether I implemented that well or not, I don't know, but that's the idea. So that as there's less and less work and threads are free, they have less and less time to find work. Because that find work kind of thing also costs you time and spins cycles, and you know, it's wasteful if you don't find anything. So you should give up earlier, and the later the threads are finishing, the more easily they give up. That's the idea, let's say. Whether it's tuned well or not, it's probably not, but that's the idea. That's what fuel is. So the first thread has a lot of fuel, and then comes the next thing. Yeah, I think it's visible in this loop here. It consumes all its fuel, or while there is fuel and while there is work, it can do what it wants to do, and it's essentially impersonating threads, other threads. And that's really the main thing that I thought is cool. When I first came up with it, I thought, yeah, so if I'm this thread, then I want to jump down to the other lane from the back of the work, because I know the other they always go in one direction, these threads. So I'm already at the end. Okay, let's use this hand. It's at the end, and this thread is still working here in the beginning. And then this one has a lot of fuel, and it says, okay, I impersonate the other one. So it could impersonate anyone, really. So the algorithm for impersonating people is pick new identity, and that really just says if it's on top, it goes down, and if it reaches some boundary, it goes up again. And that's all it does. Or it reaches some, sorry, it goes down at first, and if it reaches a boundary, it starts where it was initially, and then it goes up. So for these middle ones, right, it's not so obvious.
Yeah.
Like, where do you go? And if they are above the midpoint, it goes down. And if they're below the midpoint, it goes up. And if they reach some border, some end, then they jump to their original identity and go the other direction instead. And that's all it does. So this one would go down one level and then eat work from the end. And this is why you have the same traversal code here, but this time in reverse. And that's also cool. It's cool because these chunk IDs, they're basically computed for me by Rust, right? Because I was thinking, how do I calculate that correctly? I mean, I'm really stupid with this calculation stuff. And it's this abstraction here that really helps to have the calculation be done for you and not deal with overflow or underflow, and just have it work right, because it's so complicated to get it right. It's deceptively simple again, you know, but then again, I was trying it. This is what led me to work with iterators, because when I wanted to do the same thing in reverse that I had here, and initially I was counting by hand, you know, I was just increasing something by num threads, and now I was thinking, oh wait, how do I do this in reverse now by computation? And
yeah, it gets annoyingly complicated.
yeah, and somehow I wanted to compute it because it felt more natural, and then I realized, yeah, let's use iterators, and then this is what came out of it. And it's yeah, nice. That's the way, you know. And then everything repeats, unfortunately. Like this is a copy paste of the block above. It's the same logic. You can just refactor this and pull it out into its own method, but then you basically repeat most of this monstrosity here, like all this stuff. Most of it you repeat then, and I didn't feel like it yet. I didn't feel like it. But that might be something that happens as part of cleanup once it's proven to be working. Because it would certainly be the right thing. There's quite a bunch of logic here, but it's still manageable to just do it twice. And that's that. And that's how work stealing works this time. And you see the trade-off. There's no locking. I mean, yes, there is locking because every result here has to be locked. But that lock is uncontended. And that's a parking lot mutex. So these are really, really fast. They're faster than a standard library mutex. And they basically cost you nothing if there's no contention. It's basically just atomic in something magic, atomic something. There's not even a real mutex that is used when there's no contention or something. This is what I tested out so far. These are awesome. So it's a safety measure that you can use and that you have to use now that you are trying to steal stuff. Because there can be multiple threads now overlapping. Now the algorithm is entirely chaotic, if you so will. And this is a way to prevent them from stepping onto each other's feet, which they could otherwise.
But could it happen that two threads work on the same chunk at the same time?
No. I mean, shouldn't be, but the answer should be really no. Because before a thread is working on a chunk, it has to get the result block.
Yes, and then it knows if it's already has been worked on or not.
Yes. So we don't protect the input itself because we don't own the data. We can't just say throw a mutex in, otherwise we don't work. No. But we lock a parallel data structure that is equivalent, so to say, which is the result which we need anyway. And this also means if we wouldn't implement work stealing, we could just rely on the algorithm itself that we don't step on each other's feet, which should not happen.
It won't overlap.
Yes, but we want work stealing, so we have to protect it. But that's fast. This is why we allow mutexes here, or we use them. We have more mutexes than we have before, but they should be faster because they're not contended. And the trade-off here is literally that we have a perfect starting. You know, all the threads, they basically start at the same time. Boom. Like, sure, you have to spawn threads. This takes time, but they immediately start. They immediately get the next work. So that should save some contention. And only when they go to work stealing mode, then they might burn some more cycles on stepping onto each other's feet and trying to acquire locks around there. But they don't wait. They keep going until they burn their fuel, and then they're done, right? And this is now where a different trade-off has been made, but I have the hopes that overall it will deal better with these sub-milliseconds or these millisecond timings that we have now on these high core counts in order to, know that git oxide isn't the problem. Because there is one metric here that I would like to see changed. And that's probably then the end of our session as well, or we are nearing the end. Because the author here that made the tests on these great machines, they probably are literally great machines because I can't imagine such a CPU to live in a laptop. That's more like a tower PC thing or a rack. But this measurement here shows us that there is a whole bunch of locking going on with the mutex. And that's not so cool. So where's that happening? And I think it must be the channel, because everything else is pretty much lock free. The object database scales perfectly, and I've proof for that, because there's other parallelization code that really scales perfectly and gets 12 gigabyte per second decompression capacity. And here we just hit 1.3 gigabyte per second decompression. And that tells us, okay, it's not git oxide. In terms of ODB, ODB is not the issue, but maybe it's something else. So maybe I already kind of told myself just now that the parallelization mechanism is good enough, because we did reach, with that mechanism, we did reach 12 gigabyte per second on my computer. So apparently it's okay, but it's also different chunk sizes, and it's different. I don't know. I wasn't sure, and I wanted to implement the alternative just to be very, very sure with these high core counts, which I can't really test yet. And I just want to see if this makes a difference or not. If not, totally, archive it or something. Stick with the simple one, which has a lot of benefits. Otherwise, selectively use this where it makes sense and a difference, because it also needs you to locate this results array. You need to pre-allocate a bunch of more things. The input needs to be kind of allocated there, and so on. So it's interesting for sure, and I really can't wait to get these results and hopefully see that it then scales to, I don't know, 200 milliseconds. That would be awesome.
That'd be cool.
And then,
I mean, you already said it's gonna be, it should be a bit quicker just because of the way that the spawns, the different threads get to work and stuff like that, right?
Yeah.
So it's already going to be an improvement in that sense.
Yeah.
But if it's the one that you want, remains to be seen.
Yeah. I mean, I am kind of eyeballing this one here. Like, how do I calculate this? 748 by 0. By 1 over 100 over 60. Okay, so with this awesome math, that seems to be doing the right thing. If I had 100% efficiency here, that would be 524 milliseconds, right? And I want that on my computer, maybe. Or want to be able to say, okay, it's checking out the Linux kernel in half a second. And then put a tilde there so that it's more or less half a second. But at least I get to say half a second, because that would be such a great improvement. Just imagine, you first go well under a second, and then you probably unlock the brakes, the handbrakes finally, and then you go to incredibly high efficiency. I don't think it's going to happen because the file system still is there. But then again, the file system is also there for the 1x speed here. And it can do stuff. If one core really can do that much, then why not assume that this would scale perfectly? Why not? I don't know how file systems are really implemented, and they probably do internal locking of some sort as well to, once you write a directory, how do you do that? You need to lock it in some way in order to, not overwrite your data on disk. Writing a file system is probably another fun thing to do one day, just so that you see there's no rocket science. You still have to deal with data and blocks and locking and parallelism, a lot of that. And then things get a bit more difficult. So I think overall there must be some hard limit that you hit even with this, unless the file system is really something like dev null and you don't actually write stuff, which in my case I can even test, because I can just choose not to write anything or make a flag that doesn't really write or something just to see. But then you don't test anything anymore, because then you just test ODB performance, and we already know that this scales perfectly.
It's already done.
Yeah, so and then it's not a checkout anymore either. So it really must work on a real file system to be worth the headline. But yeah, maybe 600 milliseconds is something I can get. That's maybe still around half a second. And then this crazy
almost
machine.
half a second.
Yeah, just about. But even seeing this, that this is already the headline here. Like if I had a computer like this, I'd already be done and say, yeah.
Sure.
But I'm glad I don't. I have a slow computer, so I have to optimize things. It's
I guess this just shows, right? It's really like this under a second or half a second is really dependent anyway on the hardware. But
yes,
yeah, it sounds good.
It sounds very good and is crazy. I think Linus Torvalds is somebody who would have a machine like this, and always the latest greatest, or Threadripper or something. And he might be somebody who checks out the Linux kernel a lot. So that should be interesting. But let's see.
Sure.
Yeah, I think that is it for today. And thanks a lot, everybody, and thanks a lot, Sydney. See you next time.
Thank you very much. See you next time.